Look closely at the engine mounted beneath this wing. This is the GE9X, and its front fan spans 3.4 meters in diameter. To put that dimension into physical context, you could comfortably fit the entire fuselage of a Boeing 737 inside the outer casing of that single engine. Mounting power plants of this scale forces extreme changes to the surrounding infrastructure. The Boeing 777X requires mechanical wingtips that fold upward during taxiing, simply because the engines push the total wingspan well past standard airport gate limits. Engineers do not accept these severe design constraints to break speed records or achieve greater thrust. They push these dimensions to strictly optimize airline economics. Fuel burn dictates the financial reality of commercial aviation. For a typical airline, burning jet fuel accounts for 25 to 30% of total operating costs. This formula represents specific fuel consumption, or SFC. It calculates the mass of fuel burned per hour to produce a unit of thrust, defining commercial viability. Since early turbofans, the most reliable method for lowering SFC is to physically widen the engine. Modern engine gigantism is the physical manifestation of a singular mathematical optimization. To understand why wider is cheaper, we have to define thrust. Mathematically, thrust is the mass flow of air passing through the engine multiplied by its change in velocity. Identical thrust can be produced in two distinct ways. You can accelerate a small amount of air to extremely high speeds, or you can gently accelerate a very large mass of air. The high-speed approach carries a severe kinetic energy penalty. Because kinetic energy scales quadratically with velocity, blasting a narrow jet of air at high speed wastes a massive amount of energy as turbulent heat in the exhaust wake. This equation calculates Froude efficiency, also known as propulsive efficiency. It tracks how effectively an engine converts kinetic energy into useful forward work, based on the ratio between the exhaust jet velocity and the aircraft's forward flight velocity. The math reveals a strict mandate. As the velocity of the exhaust drops closer to the cruising speed of the aircraft, propulsive efficiency mathematically approaches 100%. To achieve that low exhaust velocity without losing thrust, the engine must ingest far more air. This is executed through the bypass ratio, the physical ratio of air that bypasses the engine core compared to the air that actually enters it to be burned. This graph tracks the history of that optimization. In the 1960s, early turbojets operated with zero bypass. Today, modern architectures have pushed bypass ratios past 10 to 1, capturing a steep drop in fuel consumption along the way. Froude's mathematics physically force engineers to build increasingly wider fans. It is the only way to process the massive volume of air required for peak efficiency. But the massive fan is only half of the equation. Driving it requires a second optimization: thermal efficiency. This schematic traces the Brayton cycle within the engine core. Thermal efficiency measures exactly how well this core converts raw jet fuel into mechanical shaft power to spin the fan up front. Maximizing that thermal conversion requires crushing the incoming air to extreme densities, pushing the engine's overall pressure ratio to new engineering extremes. In modern engines, compression ratios now exceed 50 to 1. Compressing air that tightly generates tremendous heat, resulting in turbine inlet temperatures that easily exceed 2,600 degrees Fahrenheit. That temperature creates a severe material crisis. 2,600 degrees easily exceeds the melting point of the standard metallic superalloys used to build the turbine blades. To survive this thermal environment, aerospace engineers developed a vital material science breakthrough: ceramic matrix composites, or CMCs. Composed of silicon carbide fibers embedded in a ceramic matrix, CMCs can operate 500 degrees hotter than their metal counterparts, while simultaneously weighing 1/3 as much. Because they easily withstand extreme heat, CMCs drastically reduce the need to bleed off compressed air to cool the turbine parts. That retains more thermodynamic energy inside the core to generate thrust. Without the high temperature limits enabled by CMCs, the engine core could never survive the combustion required to generate enough shaft power to spin an ultra-high bypass fan. Pushing bypass ratios to 12 to 1 solves the thermodynamic and propulsive equations, but it introduces severe physical penalties to the airframe. This curve tracks parasitic drag. Housing a massive fan demands a massive exterior nacelle, And as that frontal surface area expands, it acts like a parachute, generating intense aerodynamic drag against the aircraft. At a cruising speed of Mach 0.85, a break-even point emerges. If an engine grows too wide, high-speed drag completely cancels out the efficiency fuel savings. Beyond drag, extreme engine diameters create critical ground clearance geometry issues on traditional aircraft designs. The flight test program for the GE9X perfectly illustrates these integration hurdles. When mounted to GE's 747 propulsion test platform, the engine dwarfed original clearances. To mount it safely, engineers had to design a custom cantilevered pylon. It shoved the engine out in front of the wing and tilted it upward by 7 degrees. Even after over-servicing and extending the landing gear struts, the bottom of the GE9X cleared the runway by a mere 18 inches during tests. Engine gigantism creates a cascading series of aerodynamic and physical penalties. If the integration is not managed perfectly, the airframe drag will ruin the engine's economic viability. Inside the casing, another conflict arises. There is a fundamental rotational speed mismatch between the massive front fan and the turbine core driving it. When you expand the diameter of a fan, the outer blade tips must cover vastly more distance per revolution than the inner hub. If the fan spins too fast, those tips approach the speed of sound, triggering destructive shockwaves and immense aerodynamic drag. To remain aerodynamically efficient and avoid supersonic shockwaves, these massive fans must spin relatively slowly. This creates a direct mechanical conflict. The low-pressure turbine, located at the rear of the engine, must spin at incredibly high speeds to extract energy efficiently from the fast-moving core exhaust. Historically, the fan and the turbine were bolted directly to the same driving shaft. To force the turbine to operate at the fan's slower, safer speed, engineers had to compromise by adding heavy, extra turbine stages to extract the necessary power. This schematic details the geared turbine fan architecture, like the Pratt & Whitney PW1000G, which resolves this exact conflict by placing a highly engineered reduction gearbox between the fan and the low-pressure turbine. The gearbox physically decouples the fan from the turbine. It allows the core turbine to spin at tens of thousands of RPMs for peak thermodynamic extraction, while smoothly stepping down the rotational speed so the front fan spins slowly and efficiently. As a critical secondary benefit, slowing the fan down lowers the exhaust velocities enough to dramatically shrink the aircraft's noise footprint, allowing airlines to easily meet strict regulatory targets, like ICAO Chapter 14. Achieving the next generation of ultra-high bypass ratios required engineers to completely sever the traditional direct drive link between a jet's core and its fan. The modern Big Three engines, the GE9X, the PW1000G, and the Rolls-Royce Trent XWB shown here, are the culmination of overcoming these extreme physics constraints. Their overall efficiency is exactly the mathematical product of propulsive efficiency, achieved by the massive front fan, multiplied by thermal efficiency, achieved by the CMC-lined core. Despite the intense aerodynamic drag and the heavy airframe integration penalties, moving a massive volume of air at low velocity remains the undisputed most efficient method to achieve subsonic flight. Theorizing a perfect ultra-high bypass engine in a digital environment is only the first step. Proving that these colossal machines will not tear themselves apart on a physical test stand is another entirely.